Welcome to qnawire.
This is problem number 10 of chapter 23. Here we're asked to account for the differences in the interference pattern of the double slit and the diffraction grating. So to account for the differences, first we need to understand the interference pattern for the double slit. Here we have the double slit a distance d apart. The slits are a distance d apart, and the double slits are a distance capital L from the screen. So the distance between the slit and the screen is L. Constructive interference occurs when the path length difference from the top slit and the bottom slit, the path length difference is an integer multiple of the wavelength. So if we represent the path length difference by a symbol, delta, constructive interference occurs when this path length difference is equal to an integer multiple of the wavelength. Now why is that? Well, let's suppose light is traveling from this top slit to the screen, to this point, let's say, here at the center of the screen. Let's suppose it's going like this until it reaches the screen. Now, since we are looking at this central point, the zero order bright fringe, the light from the lower slit is going to be in phase with the one from the top of the slit. So by the time they get to this point here, they're going to be in phase. So peak is going to match with peak, and then you're going to get constructive interference. The sum of these two waves is going to result in a bright fringe here at the 0th order. With ray diagrams, we could express that as, here we have a light ray going from the top slit to this point here on the screen, and that 0 order bright fringe is going to occur when the path length difference between this red ray and this blue ray, if that path length difference is 0 times lambda, or if that path length difference is 0, the two waves are in phase and you're going to get destructive interference. So this is going to be the 0 order bright fringe. For the 1st order bright fringe, again, it has to be an integer multiple of lambda. So if the path length difference is lambda, then we were also going to get constructive interference. For the 1st bright fringe, it's going to be somewhere out here, but again, this screen is much further than the separation here between the slits. So when viewed from the slits, if we're going to the 1st bright fringe, since the screen is so far away, the light aiming to that 1st bright fringe, it's pretty much going to be parallel. So if this light goes in that direction to the 1st bright fringe, here from the top slit, it's going to be parallel to it, because the screen is not really here. The screen has to be much further away. The path length difference then can be calculated if we draw a perpendicular line from this top ray. So we go ahead and draw a perpendicular line from here to here. That distance from the bottom slit to this intersection, that's the path length difference. So notice that since we drew a perpendicular line and this red line and the blue line are parallel, this purple line is also perpendicular to the blue line, so that's 90 degrees right there. We're going to define the angle between this black line and the purple line as theta. So here, let me label theta in green. This is going to be theta. Here we see that sine of theta is going to be opposite. So sine of theta is going to be opposite, which is the path length difference, over the hypotenuse, which is d. We multiply d on both sides, and this is how we get d sine theta m is going to be equal to delta. For constructive interference, delta is just going to be equal to m lambda. So that's where that familiar equation comes from, provided that m again, it's an integer multiple, so it's 0. 0 is included because the 0th order bright fringe leads to a delta of 0, so constructive interference occurs. So M is limited to that. For destructive interference, notice that the geometry is going to be the same here. However, for destructive interference, delta is going to change. For destructive interference, delta is going to be equal to an odd integer multiple of half wavelengths. So here, M is going to be restricted to odd integers, so 1, 3, 5, 7, etc. Other than that, this equation is still going to apply, so it's going to be d sine theta m equal to the path length difference for destructive interference, where m is limited to odd integers. From these two equations, we see that here on this screen, there's going to be points there's going to be clearly defined points of constructive interference and destructive interference. Their exact locations are going to be determined, again, since this screen is located so much further away from the slit, this angle theta, it's actually going to be very small. So if we draw a line from the center of the slit here, let's go ahead and draw it like this, to the 0th order bright fringe as our reference point, any angle to the other order bright fringes, let's say the 1st order bright fringe is here. This angle formed between this light blue line and the green line is going to be a small angle. Here, this distance, we could call it ym, y sub m. So again, from the geometry, we see that tangent of theta m is going to be equal to y sub m over L. Now for small angle approximations, tangent is going to be approximately equal to sine, and then we could use this information to find the exact location of these bright and dark fringes. So the point here is that the bright and dark fringes are clearly defined here. In the intermediate, so we're going to have a series of bright spots. Let's say, so let me go ahead and symbolize the bright spots. Let's say the bright spots are red here. We're going to have a series of bright spots. In between these bright fringes, we're going to have dark fringes. So let me go ahead and mark those. And between each bright and dark fringe, we're not gonna get a completely destructive interference, and we're not gonna get completely constructive interference. We're gonna get something in between. So when waves arrive at a bright spot, they are in phase. When waves arrive at a dark spot, they are completely out of phase. In the intermediary points, they are not going to be completely out of phase, and they're not going to be completely in phase. So that's why we're going to see wider bright fringes and narrow dark fringes here, because the only time we're going to see a dark fringe is if they completely are out of phase, and that only happens at these points. The only times we're going to see completely constructive interference is when this is satisfied, so that's going to be the bright spots, but in a point in between, it's not going to be completely canceled out, it's not going to be completely constructive, it's going to be somewhere in between. So that's why the interference pattern observed on the screen, so we're going to get a bright spot here at the center, it's going to go down to a minimum here, and then it's going to bounce up like this. So represented graphically, it's going to look something like that. And then this is going to be symmetric about the 0th order bright fringe. Okay. So this is the pattern observed for the double slit. We're going to have wide bright fringes, narrow dark fringes. So why would this change for the diffraction grating? Well, the difference between the double slit and a diffraction grating is that we're going to have more holes. So if we have more openings here, let's say we have another opening down here, so each one separated a distance d. Let's go ahead and draw the openings for diffraction grating. So let's go ahead and copy this, and let's go ahead and make a diffraction grating here underneath this, and let's see why that's going to cause our interference pattern to change. Okay, let's go ahead and start labeling our different openings here. I'm just going to put little tick marks. So here are 2 openings, and let's keep this distance, so let's make more openings here. Okay, each little line here is going to symbolize an opening. So we're going to have a bunch of openings. Okay, so this is no longer the double slit, this is a diffraction grating where each of these ticks symbolizes a new opening. Okay, we already analyzed these 2 light rays emanating from these 2 openings. Let's see what happens if we look at another ray emanating from this bottom one. So let's go ahead and erase this. Let's see what happens if we shoot another ray from here. And let's suppose that this is aiming at that first bright fringe as well. So we already talked about these first 2 light rays aiming at the first bright fringe. We're just now looking at a third one. Notice that we can also draw a perpendicular line here, from here to here. Now, I didn't draw this perfectly, so let me move this down. The next line is supposed to be. So let's suppose I drew this perfectly. So let me just go ahead and copy this. That way I have it exactly. I have the next opening exactly where it needs to be. So if the slits are a distance d apart, the next one is actually supposed to be down here. Okay, that's better. The distance between these 2 is d. The distance between these 2 is also d. So notice what's happening here. This distance, since this distance is d, the distance between the opening of this third slit and this intersection, that's going to be it's going to be the same delta as the one here. So if these 2 constructively interfered, these 2 blue lines are going to constructively interfere. And if these 2 constructively interfere, then this blue one would constructively interfere with the red one. So combined, they are all going to constructively interfere to produce a bright fringe on the screen here. So let's go ahead and eliminate these. On the screen, what we're going to see is a well-pronounced first bright fringe. So we're going to see something like this, a well-pronounced first order bright fringe. Okay, here let's suppose that we have another ray coming from the next lowest, actually let's go higher, let's go here. If we go 1 higher, okay, the next opening should be somewhere up there. If I want to keep the distance between the slits constant, it's going to be right here. Okay, and let's analyze the ray coming out through here. Here we are. It's going to be parallel to the other ones. The reason it's going to be parallel is because this screen is really way out to the right. Notice that the path length difference is from the opening of this slit to the intersection here. This path length difference is the same as the one we analyzed initially. So if the red ray and the blue ray are in phase, then the red ray is in phase with this green ray, is in phase with this light blue ray. They're all in phase and they're all going to interact constructively here for this bright fringe. This argument can be repeated for any of the other bright fringes because constructive interference occurs when it's an integer multiple of the wavelength. Now, why is it that for the diffraction grating we're going to have narrow bright spots and wide dark spots? So let's think about that. If we vary here if this ray goes out to the first bright fringe, it's going to be in phase with the one below it. It's going to be in phase with the one below that, in phase with the one below that. So how can we represent that graphically? Well, if we have a light wave like this, for the green ray and the red ray to be in phase, what that would entail is that this peak from the red ray must coincide with the peak from the green ray. So they're going to arrive in phase. This is what's going to arrive here on the screen. This is what's going to arrive here on the screen, and they're going to be in phase. Now, what would happen if we go a little bit off to the side here? Off on top of the bright fringe. So just a little bit on top of that. Well, the distance between this first bright ray, this bottom ray, the path length difference is still marked by this one here. However, the distances are gonna be slightly, so for destructive interference, that's only gonna occur if they are out of phase by integer multiples of half wavelengths. Just off center here, if it's 1.1, let's say, if we are just north of this first bright fringe, that means that even though this red ray is gonna, when it reaches that point, it's not gonna be precisely at the maximum, because if the maximums are the bright fringes, it's gonna be a little bit off, and then here the green ray travels a little bit less than it. So let's suppose that the red ray is right here, the green ray is going to be a little bit less. Let's say it's going to be right here. So they're going to be constructive, but not completely. But as we keep on analyzing the other ones, these other rays, as we keep on going down the diffraction grating, eventually we're going to reach one ray which completely cancels out the contribution by the red ray. So the contribution by the red ray would be given by, okay, so here the red ray is aiming down, so the negative contribution, the one that would precisely cancel out, would be some ray out here, and that contribution is going to be given by some slit up here. So there's going to be some slit such that the light coming out from it is gonna, the path length difference between these two, between this orange line and the red line, the path length difference is gonna be precisely out of phase, just enough to cancel the contribution by the red ray. And the same thing is going to be said of the green ray and so on, because there's so many more openings there. There's going to be one that's going to cancel it out. So that's the reason that the bright fringes are narrow and the dark fringes are wide, because there's so many openings here in this diffraction grating that eventually there's going to be one light ray that completely cancels out the contribution from the one that we're looking at. And this is going to be just off the center of the bright fringes. So let's see if so here we have this orange light ray. This is not going to be exactly this distance away from it, but if we were to draw a perpendicular line here from this one to the red ray, there will be one light ray such that this path length difference is going to be an odd integer multiple, half a wavelength, to completely cancel the red ray out. And since there's so many slits, there's going to be a pairing for each of these other light rays such that they are canceled out at all these other areas. The only exception is going to be for the bright fringes where constructive interference occurs.